This video covers elementary steps and the collision model. By the end of this video, you should understand what an elementary step is, understand the factors that determine whether a collision will produce a reaction, and be able to use the collision model to explain why various factors will affect the rate of a reaction. We'll be learning about reaction mechanisms in future videos, but for right now, looking at some basics about reaction mechanisms will help us understand what an elementary reaction is. So most reactions, when we look at a balanced equation, it looks like it occurs all in one step, but that's not true. Most reactions actually occur in a series of small steps or events. If we add up those small steps or events, they lead to, we call that a reaction mechanism. So for instance, consider the decomposition of ozone into oxygen gas. This does not happen in a single step. Ozone does not, in a single event, convert to oxygen. Instead, it happens in a two-step mechanism. First, the O3 breaks down into O2 and alone oxygen, which, as you probably know, is pretty unstable since it is not combined with another oxygen. So that oxygen is quickly consumed in a subsequent step where it combines with another O3 to give us two O2s. Each of the two steps in this mechanism is called an elementary step because it happens in a single step, whereas the overall reaction, as we can see, happens in two steps. Elementary steps should be able to sum to the overall reaction. That should make sense if the two steps should lead to the finished product. So let's look at how this works here. In this case, the oxygen produced in the first step is consumed in the second step, so we can cancel it out. Another way of thinking about this is it appears on both sides of the arrow, so it's going to cancel. That leaves us with two ozones on the reactant side and three oxygens on the product side, and we see here that the sum of this mechanism is the overall reaction. So that overall reaction actually occurs in two smaller steps. Notice that this mechanism also includes an intermediate. An intermediate is a species that forms in one step but is used up in the next. In this case, the lone oxygen was formed in step 1 and consumed in step 2. That's an intermediate that you would not see in the overall balanced equation because it forms and then is immediately consumed. But when we're looking at the steps that make up a reaction, those intermediates are important. A few more things about elementary steps before we proceed. First, as implied by the name, and as we've said, they occur in a single event or step, meaning they are the result of a single successful collision between reacting molecules. Recall that only a small fraction of collisions actually are successful in that they cause bonds to break and reform, resulting in a reaction. So let's remind ourselves what the factors are that will cause a collision to be successful. For this, we need the collision model. The collision model basically says that molecules have to collide to react, right? And remember that only a small fraction, again, of those collisions will be successful. There are two factors that determine whether the collision will be successful, will be effective, will produce a reaction. The first is the collision has to have enough energy, and the second is the molecules have to have the proper orientation. So let's consider the first requirement, energy. Molecules must collide with enough kinetic energy to break the reactant bonds. Remember, we have to break reactant bonds in order to form new product bonds. So, upon collision, the bonds within the reactant molecules stretch, bend, and ultimately break. The molecules have to collide with enough energy to do that. We refer to this energy as the activation energy, abbreviated EA, big E, little a. The activation energy is the minimum energy needed to get the reaction going. It's the minimum energy needed for the reactants to collide and actually produce a reaction. This will vary from reaction to reaction. It's often thought of and talked about as an energy barrier, meaning you have to overcome the activation energy barrier in order for a reaction to happen. Collisions could be occurring, but if they don't have sufficient energy to overcome the activation energy barrier, nothing's going to happen. It should be pretty intuitive that at a higher temperature, represented by the red line here, more collisions will have enough energy to actually be successful. In this graphic, you're seeing the dotted line here is our activation energy barrier, the minimum energy needed for a reaction to be successful, or for a collision to be successful. At a lower temperature, most of our particles have a pretty low energy, so they're not going to collide with enough energy to produce a reaction. A small fraction will, but not many. As the temperature goes up, a larger fraction of those molecules of those collisions will have enough energy to overcome the activation energy barrier. The other requirement is molecular orientation. In this case, we're looking at the formation of CO2 from CO and O2. In order for CO2 to form, an oxygen from the O2 has to collide with the carbon from the CO. If they collide in the proper orientation, meaning the carbon is in contact with the oxygen, then a reaction will occur. If they don't collide in the proper orientation, meaning the two oxygens collide with each other, we will not get a reaction. Another factor to consider when thinking about how likely a reaction is to occur is the molecularity of the elementary steps. Molecularity refers to how many molecules are involved in the elementary reaction. So let's consider first a unimolecular step. This would be a reaction in which only one molecule is involved in the elementary step. In other words, H3CnC. That's a single molecule. It will collide with other molecules of itself. Some of those collisions will be effective in that they have enough energy and the proper orientation. And in fact, actually, energy is the most important thing here. And the bonds will be able to break and we'll get reactions. That's pretty easy because there's not many requirements, right? There's a single molecule, it's going to hit other molecules. Compare that to a bimolecular elementary reaction where you need two molecules to collide in order to produce a reaction. Here, NO and O3 need to collide. So now we're dealing with two molecules having to have the right amount of energy and the right orientation. So that's going to be a little harder than a unimolecular reaction. And finally, a trimolecular would involve the simultaneous collision of three molecules. That's pretty unlikely. Think about what that would require. It would mean that three molecules would have to collide with each other with enough energy and in the right orientation to produce a reaction. That's pretty unlikely, not impossible, but pretty unlikely. So those often do not happen in a single step. They would be broken up into several elementary steps. Now let's think a little bit about some factors that will affect the reaction rate, keeping in mind all the while that collision theory underlies all of this. So anything that will change the frequency of effective collisions will change the reaction rate. So reactant temperature, reactant concentration, presence of a catalyst are the three major factors that will affect the frequency of effective collisions and thus the reaction rate. They're not the only ones, but they're the most common. Let's look first at temperature. We already discussed this briefly. At a higher temperature, more of the collisions will have sufficient energy to overcome the activation energy barrier. At a lower temperature, fewer collisions will have enough energy to do so. Moving to reactant concentration, if there's more reactant molecules in a given volume, you're just going to have more collisions, right? If there's more molecules there, they'll collide more frequently. If you have more collisions, the likelihood of you having effective collisions is going to be higher, right? More collisions means that more of those collisions will have the right orientation, right? The more times you play the lottery, the more likely you are to win, right? So that will result in a faster rate. Looking at this graphic here we have very few molecules, right? They're not going to hit each other all that often. Put more molecules in the same amount of space and we'll get more frequent collisions, meaning we'll have more effective collisions and a faster rate. Note that we can get to a higher concentration two ways. Here we've done it by adding more molecules to a given volume. We could have also taken this container and made it smaller with the same number of particles. That would also increase the concentration because while you're not changing the number of moles of reactant, you are decreasing the volume. So that's another way to get to a higher concentration. And finally, presence of a catalyst. More on this later. There's a whole video on this later. That brings us to the end of this video. Let's review our goals. First, we learned what an elementary step is. It's a step in a mechanism that occurs in a single event. Then we looked at the factors that will affect whether a collision will produce a reaction. And then we looked at how the collision model informs and explains why these factors will affect the rate of a reaction.